Welcome to homework.
This is the answer to chapter 23, problem number 19 from the Smith Organic Chemistry textbook. This problem asks us, how can 2-pentanone be converted into each compound? And so basically, looking at all four of these compounds that are our target molecules for this problem, they all have more carbons than 2-pentanone. And so a way that we know now to add carbons to a molecule that has a ketone or an aldehyde or any carbonyl really is to deprotonate at the alpha carbon and then alkylate. And so that's going to be the general strategy that we pursue in this problem. And so with that in mind, for A, first we're going to treat A with LDA in THF, and that is going to deprotonate that terminal position, since that is the less hindered position. And so that's going to give us this carbon ion with the lone pair, as I said, in the terminal position. And then we need to add 2 carbons. We need to add an ethyl group to get to our desired product here. And so we can just do that with ethyl bromide. And so after treatment with ethyl bromide, we are going to be at our target endpoint. Okay, so there we go. There's A. So for B, we're going to pursue a similar strategy, but we're going to want to deprotonate at the interior alpha carbon instead. And so to do that, we are going to use potassium tert butoxide. And we're going to use T-butanol. So potassium tert butoxide and T-butanol are going to deprotonate the interior alpha carbon. So we have our lone pair and our negative charge there now. And now we can use methyl bromide to add a methyl group. Okay, and we want the dimethylated product. And so we can just follow the sequence a second time. So another equivalent of potassium tert butoxide in T-butanol. Is going to deprotonate that same carbon once again. So now we have a methyl group there. So it'll deprotonate. We'll get our negative charge there. And then again, to add a second methyl group, we just need to use methyl bromide again. Okay, and so there is our product for part B. So for part C, we're actually going to start from the product that we made in part A. And, same exact strategy, LDA and THF to deprotonate. And both of these alpha carbons are equivalent in this molecule. So it's fine to use LDA and THF. There's no selectivity issue or anything. So that's going to deprotonate the alpha carbon. And then we are looking to add a methyl group. So we can use a methyl halide. Let's use methyl iodide this time. Okay, and so there we are. There's the answer to part C. For part D, we're going to start from one of the intermediates in part B. And so in part B, we had this intermediate at one point, and we wanted to add another methyl group to that same interior alpha carbon. So we used potassium tert butoxide to selectively deprotonate that interior alpha carbon. But this time we want to add a methyl group to the other alpha carbon. And so we can accomplish that with LDA and THF. Okay, and so we've deprotonated here now. So there's our lone pair and our negative charge. And then to add a methyl group, we can use another methyl halide. So let's go back to methyl bromide. Okay, and so we've added that methyl group there now. And this is our, I missed. There we go. This is our desired product for part D. Okay, and so that's just 4 examples of the utility of this strategy of alkylating an alpha carbon by a sequence of deprotonation with a strong base, so LDA or potassium terpbutoxide, and then treatment with an alkyl halide to add the alkyl group of the alkyl halide to the alpha carbon that was just deprotonated. And that's the answer to chapter 23, problem number 19.